the class. So here you can write this as the six different terms over here, and those six different terms will just straight away correspond to, if you just see there, will just straight away correspond to the six terms which we might have written over here. Okay, this itself is written in a different way there as a six different determinants here. Six different determinants here. So out of many different determinants, only n factorial out of n by n, n to the power n, that means when we have 3 here, then it will be 3 to the power 3, that will be 27. Is it 3 to the power 3 will become how much? 3 to the power 9. 3 to the power 9 will be quite heavy. So many determinants, only n, that is 3 factorial, that will give you just 6 determinants will be non-zero. All others will become 0 because a column is repeated. That means when you consider this here, okay, when you consider a particular row, then options are you can have any one of the column elements. If I take row 1, then I can consider any one of the columns. But once that is over, then what you call for the next row, if I go, then that column is over. The rest 2 columns will come into picture. So that is what he's telling here. So you can see here that there are n choices for the first column alpha, n minus 1 remaining choices for beta, and finally only one choice for the last column v. So if once one column is over, you can't repeat that. That means if I try to take this element here, this column and this row will go. So I should talk only with this 2 terms over here. So I have only a11, a22, a33, and then a11 to be multiplied with these 2. Okay, a11 multiplied with these 2, and then a11 multiplied with these 2. Of course, this multiplied by this will be with a positive sign, whereas this and this multiplied will give a negative sign. We know that very well in finding the determinant. Similarly, when I try to multiply with this, a minus will come before this itself when you find the determinant. That multiplied by this and this, then this after that this multiplied by this, and this will have a minus sign, and this also will have a minus sign, hence it will become plus. And that is this term which we might have written over here. So first term which we have written there is corresponding to a11, 22, a22, a33, that is this one. Then a12, a23, a31 is what we have written here. And then we have written the a13. a13 is to be multiplied with the value a21 and a32. That is what we have written here. And similarly, we are trying to write the other terms as well. So then we are going for a11. a11 is multiplied with the a23 and a32. So that means with a11 we are writing these 2 terms. With a12 we are writing these 2 terms. If that is for the last one, that is a13 here is getting multiplied with the corresponding values over here and here with the corresponding 2 terms. Okay, so the choice will be first we can say that there are n choices for the first column. If I want to take the first column, I can take either the first row or the second row or the third row. Then for the remaining what you call columns, we might have the n minus 1 rows choices, and then finally only one choice for the last v. So therefore 3 into 2 into 1 is the determinant number of determinants we might have. So in other words, there are n factorial ways to permute the numbers. Now this can be considered in a different way like this. That is, we have written here alpha, beta, v, 1, 2, 3, 2, 3, 1, and all that. And how did we write that? If you see here, this is 1, 1 will come here. Then 2, 2 will come here. 3, 3 will come here. Then 2, 1 is what we might have written. 2, 1 over here. This 2, 1 is, I think, might be, considered here. So you can see that this is, rather the other way around. You can say 1, 2, 2, 3, 3, 1. 1, 2 is here. 2, 3, 3, 1. 2, 3 and 3, 1. Then again, for the third determinant, we'll have 1, 3, 1, 3 here, 2, 1, 2, 1 here, and 3, 2, 3, 2 here. Similarly, all the others. So thus we'll have this 6 different permutations, 6 different permutations of the different possibilities of the combination of rows and columns. So there are 3 factorial equal to 6 permutations of 1, 2, 3. The first one is the identity, that is, which corresponds to the identity matrix 1, 1, 1. So we can just take out the common value. The determinants of A is now reduced to 6 separate and much simpler determinants. So factoring out the Aij, there is a term for every one of the 6 permutations. So if you take out that, factoring just means you take common value, then we'll get 1, 1, 1. If you take out this common value, you will get 1, 1, 1 at these different positions. Similarly, at different positions, you'll get 1, 1, 1. Now, each one of this quantity might be a, if you take the determinant of this, it will be 1. If you take the determinant of this, again it will be a plus 1. If you take the determinant of this, again this will be a plus 1. But the determinant of this, determinant of this, determinant of this will be minus 1. You can try to find out that. So every term is a product of n equal to 3 entries Aij with each row and column represented once. If the columns come in the order alpha, comma, dot, 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 v, that term is the product A1 alpha, A and V times dot, 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 A and V times the determinant of the permutation matrix P. So the determinant of the whole matrix is the sum of these, n factorial terms, and that sum is the formula. You can write that as the, you can write the short form for whatever we have written here. So whatever we have written, see, this is just a permutation matrix. All these are permutation matrix, which can be either 1 or minus 1. The determinant value will be 1 or minus 1. So determinant of permutation, and this quantity is just the multiplication which corresponds to A1 alpha, A2 beta, dot, 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 A and V for all P's. So determinant of A, which is there over here, is just the, the sum of all the possible values of, A1 alpha, A2 beta, dot, 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 A and neta. So for an n by n matrix, this sum is taken over all n factorial terms. So if you have a 3 by 3 matrix, this will become 6 terms. If it is 2 by 2 matrix, it is only 2 terms. If it is 4 by 4 matrix, it will be 4 factorial, and that will just correspond to 24 terms and so on. So that will give us the permutations, n factorial permutations, alpha dot 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 neta of the numbers 1 dot 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 n. So the permutation gives the column number as we go down the matrix. The ones appear in P are the same places where the A's appeared in A. So wherever the A's are there here, correspondingly the ones are appearing only at those positions. Now we need to find out that the determinant of P will be always equal to either plus or minus 1. So row exchanges transform it to the identity matrix, and each exchange reverses the sign of the determinant. So what that means is, if you take over here, if you take this over here on the whole, so the determinant of this is 1. From here, if I want to come to this, from here, if I want to come to this, then I need to shift it, 2 times. How do I shift it here? I can take, somehow, the third row and the first row can be exchanged. First row and third row can be exchanged. Then this one will go here. This one will come here. Then the second row and the third row will be again exchanged, so that I'll get one here will be because of this, one here which is coming to this and then coming to here, one this coming down here. So from here, if I want to get this, I need to, what you call row exchange, I should do twice for this. First between R1 and R3, then between R2 and R3. So if you shift it, do the row exchange twice, it will not change the sign. Even number of times if you do the row exchanges, it will not change the sign. But if you do odd number of times, then that will change the sign over there. So here, if you see, if I want to take this, bring this in this form, then these two, row 2 and row 3 have to be exchanged. Okay, row 1 position is same here, 1, 1. Only these two are at 2 different positions. So I need to exchange these two. So that will give me the diagonal, identity matrix. Similarly, to bring this into this position, I might need to do only once or might be thrice. You just need to check, how much that value will be. Okay. So similarly, you can check all that. So which is there here? If you see this third one is same as this. Only these two have to be exchanged. R1, R2 have to be exchanged so that we get back this. Similarly, if you see over here, right? Now the second one is row 2 is at its proper position, but row 1 and row 3, if you exchange this, you'll get back this. So that means once exchange of this will get us there. Once exchange of this will get us here. One exchange of this will get us here. One exchange of this will get us here. Two exchange of this will bring us to this position. Similarly, two exchange of this will bring us to this position. So two exchange means no sign change. One exchange means there will be a sign change. That is what is permutation. So that's why we'll have the determinant P will be either +1 or -1, depending upon whether we have even or odd number of row exchanges. And the same thing is being explained over here again. So for n equal to 2, we only have 1, 2 and 2, 1. Only two permutations are there. So determinant of A is A1, 1, A2, 2, determinant of this quantity, plus A2, A1, 2, A2, 1, determinant of this quantity, which will just turn out to be A1, 1, A2, 2 minus A1, 2, A2, 1. And this we have already written in the form of AD and BC. Okay, in these positions, we might have written AD and BC. So for A equal to I, if we have a matrix A as a identity matrix, every product of Aij will be 0 except for the column sequence 1, 2, 3, n. That just means that the diagonal, okay, only the diagonal exists in I. So product of all the diagonals will just give us the value 1. So this term gives the determinant of I as 1 into 1 into 1 into 1 and all that will just give us 1. So the determinant should depend linearly on the first row, A11, A12 and A1n. So this is rather important. Determinant should depend linearly on the first row. Correspondingly, it can be dependent on the first column also, because column and row are just transpose of each other. So using this, we are trying to multiply the other in the expansion. We might be trying to use this as the initial element, and then we might be trying to look at the others. So if you look at the terms A1 alpha, A2 beta, till A and B involving A11. The first column is alpha equal to 1. This leaves some permutations beta to V of the remaining columns 2 to n. So if you take alpha equal to 1, then the remaining beta to V of the remaining columns can be corresponding to 2 to n. All these terms are collected together as A11 into C11. We generally write A11 into the cofactors of 1, 1.